much better job. I mean, if the universe was made for us, why can't we live in space? God's perfect. He could have made us live in space. Why did he restrict us to this crummy little planet? Now, let me get to some of the technical points that people who make the fine-tuning argument use. First, I want to start with 4 extreme examples, and I'm only going to discuss 2 in detail. Now, it's pretty clear that you can use the argument that while most of the theists who use this fine-tuning argument are thinking of our kind of life, because they think that humanity is special, we're made in the image of God, presumably meaning we've got his DNA and everything, that there could be other forms of life, obviously. I mean, just think about it. Even my 9-year-old granddaughter was in a class one day, and they were talking about this, and she said, I don't see why, just came to her head, I didn't talk to her. She lives in Hawaii. I only see her once a year. And she said, well, I don't see why there couldn't be other forms of life. However, the people who claim fine-tuning have come with these 4 numbers that they say without which are so fine-tuned that if they weren't exactly what they are within one part in a huge number, would life of any sort would have been possible because the Earth would not have formed, the universe would collapse immediately, and so on. And here are the 4. The gray ones are ones I'm not going to talk about. Actually, there's 5. But the darker ones I will talk about. The ratio of electrons to protons, I'll just give the answer to that later. The ratio of the electromagnetic force to gravity, expansion rate of the universe, the mass density of the universe, and something called cosmological constant that was in Einstein's general theory of relativity. These are 4 parameters of the universe that are said to be fine-tuned to 1 part in 110 to the 20 or something, 20 to the 120. Let's talk about gravity and electromagnetism. Now, I must say that in all the years I was teaching physics, I made the statement many times, as does every other physics professor and physics teacher, even high school physics teacher. They always say the same thing, that the electric force is 10 to the 39 times stronger than the gravitational force. You hear that all the time. Gravity is so weak. The electric force is so strong. And this is a big puzzle. Why should it be? Why should that big difference be? But I want to point out something that I just realized only when I started thinking about it, and that this number, 10 to the 39, is calculated as the force difference between the ratio of the electric force to the gravitational force for an electron and a proton, separated by some distance r. Since they're both 1 over r squared forces, r doesn't matter, but it does depend on the charges of the masses. If you had 2 particles, each of the same mass for simplicity, each of the same charge, mass m, charge q, you would get a different force ratio of forces depending on m and q. For example, let's let q be the unit electric charge, same as the electron and proton have, E, and let's let the masses be 10 to the minus 8 kilograms, which is a very basic mass. It's called the Planck mass. It's actually the only natural mass that you can form from basic constants. In that case, the gravitational force is 137 times bigger than the electrical force. In other words, there isn't any way to define the ratio of the strengths of gravity and electromagnetism. It all depends on the numbers that you put in. So the puzzle is not why the electric force is so much stronger than the gravitational force. It is for normal particles like electrons and protons. So the real puzzle is why are the masses why are the masses of fundamental particles so small compared to the Planck mass, which is, as I said, the only natural mass that you can form from the basic constants of physics. And there's actually, within the standard model of particles and forces, which was developed in the 1970s and has been tested now for 40 years, and it hasn't failed the Stenger test yet. However, we now have the Large Hadron Collider in Geneva going into operation, and we expect to be able to see finally what people have been looking for many years. The way physicists are, they don't like everything to work. They want to know.